Analytical and environmental chemistry mark our first excursions into labs where we have a lot more independence than we're used to. We'll be working with a much wider variety of molecules, and while our priority is always to use the safest procedures possible, there are a wider range of risks that we'll encounter. On primary containers, these risks are often indicated with the GHS, or Globally Harmonized System. These symbols are meant to give you a very visible indicator of what you should keep in mind when using a reagent or disposing of its waste. The most common hazard label is flame, shown in the top left. The flame is an indicator of the inflammability of a substance. Most organic reagents have high flame ratings, so many of you have seen this before. A flame over a circle indicates an oxidizer, like an O for oxidizer. This means that it can remove electrons from other molecules, and we generally want to keep oxidizers separate from those molecules. The oxidizers should not be stored near the inflammable substances under any circumstances. So flames and the flames of the O should never be near each other. The hazard label on the top right is an exploding bomb, indicating something is unstable or self-reactive. Generally, I avoid these even in the advanced labs. These need particularly special care. Although on a side note, one of our graduates works to test chemical hazards like flammability and temperature stability. So it's not to say that we don't prepare you for special handling. In the second row, we have the corrosion indicator, which is a picture of a substance dissolving the table or a person. These are often strong acids or bases, which we will use in lab. Gas cylinders are reserved for cylinder gases. We have a few in the lab, argon tanks for our microwave plasma instrument, and helium for our gas chromatograph mass spectrometers. These are strapped for safety, so you shouldn't need to worry about these hazards, but there are special handling instructions for cylinders. The skull and crossbones hazard indicates booty attractive to pirates like gold or silver, or possibly toxicity like a poison. You get to guess which one. In the bottom row, there is an exclamation mark used to indicate a lower level of risk than corrosion, or the skull and crossbones, or the health hazard, which we can see on the bottom right. The health hazard is for the things that won't kill you outright, they'll just destroy an organ or give you cancer. Our final symbol in the bottom center is the environmental hazard symbol. This designates how we should deal with our waste. This symbol indicates that if we flush this down the drain, all the trees and all the fishes will die. As the fish die, they will also begin looking more like goldfish crackers than real fish, creating a secondary hazard. We don't want that, so we'll take proper care of our waste. These labels may sound scary, but the risks are most significant if they're not controlled. We can use flammable substances in fume hoods and keep our hair tied back near flames. We can store oxidizers properly, use gloves when using corrosives, and keep all food and drink out of lab, and always wash our hands before we leave to dramatically reduce risk. In addition to these, we will always wear goggles, clothing that covers our legs, and closed-toed shoes. And most of the time, we won't eat our reagents. In addition to the GHS symbols, hazard information for any individual molecule can be found using the MSDS, or just SDS, which stands either for Material Safety Data Sheet or just Safety Data Sheet. You can find all of them digitally through TrollWeb. Navigate to the physical plant portion under Departments, and the MSDS online service is the only thing that has an awesome icon. It is, after all, a Velocity EHS solution. Try searching for the dichloromethane MSDS online using this service. It will default to a products page, but you should be able to find View PDF in the top right. See if you can identify one potential health hazard for dichloromethane. I hope it doesn't come as a surprise to you that our course comes with a significant number of measurements, and we will primarily use SI units, which stands for System International, or however you pronounce the equivalent in French. In this course, we will use each of the top 6 units, or derivatives, really frequently. Each of these base units is described in relationship with a physical constant. This table is actually dated. As recently as 2019, a kilogram mass was defined as the exact mass of one individual physical object stored in France. Since May 2019, the kilogram is actually defined in relationship to Planck's constant. We will not use candelas in this course. We will also sometimes use derived units, which are related to SI base units through maths. We don't actually use them differently in most cases, except that if we know a unit has a derived definition, it sometimes helps us to do our dimensional analysis. For example, a watt, the derived SI unit for power, is actually the same as a joule per second. If you want to know how much energy a 100-watt light bulb uses, you can use the fact that 100 watts is 100 joules per second to let us know that we need to multiply by time to get the energy units of joule. No measurements we can do can ever be exact, except for a count, which means we're always going to be estimating a number. The tool we will use will often determine the precision that we can give, but it's also important to convey what we know about precision right in the numbers that we report. It's kind of like looking at a jar of M&Ms and trying to guess how many are in each jar. Any individual will guess the number of candies in each jar, but most guesses are only going to be accurate to the hundreds unit, and the tens in one unit will probably be estimated. So we might be fairly certain that there are about 600 M&M minis in the left jar, but we'd have to guess at the 10 in 1 units. I might guess 615, but I really only know with any reasonable certainty about the 6 unit, and the 1 and 5 are both estimated. You might estimate 623, and you would be equally justified in that. Significant figures allow us to indicate this precision right in the number. The very last significant figure given is always the first estimated digit, the one that you aren't sure about. So significant figures will record every digit that is known fairly certainly, and then one estimated or uncertain digit. On the graduated cylinder that's shown on this slide, the two certain digits are 9.6. Notice that the graduation is going from 9 up to 10 as you go down. You can clearly see that the liquid falls between the 6th line down from 9 and the 7th line down from 9. But there are no markings between the line indicating 9.6 and the line indicating 9.7, so you need to estimate the last digit. So I think it's 8/10 of the way down, meaning the measurement I'd give should be 9.68. If you thought it was actually 9.69, that would be a reasonable estimate for the same thing. If you thought it was 9.61, you're probably thinking about the lines backwards. You sit on a throne of lies and the truth is not in you. An analytical balance is even easier. You should record the last digit as the uncertain digit, even if it's a 0. If you're getting variation at a higher digit, then the scale probably isn't calibrated properly anymore. We can talk about how to fix that. On a volumetric flask, the uncertainty is actually written on the flask itself. Calibrated autopipettes or micropipettes have the uncertainty indicated by the scale on the micropipette only at the top of their capacity, like in the range of 800 plus microliters for a 1,000 microliter pipette. The lower in the range you go, the more percent variation there is. So it's always best to use the minimum volume pipette possible. You're going to get more accuracy from a 200 microliter pipette at 200 than you would from a 1,000 microliter pipette. It's also worth noting that if you record a measurement with too few or too many significant figures, it will convey false information about how much you know about a measurement. It's a lie. Don't lie. To avoid this, in high school chemistry or general chemistry, we told you that scientists use scientific notation. That's also mostly a lie. Most scientists prefer to use metric prefixes to put something in an appropriate scale. So like 100 milliliters is often what we'd say instead of 0.100 liters. Which measurement will allow for the reporting of more precision if reported to the proper number of sig figs? A 1 or a 0.9? The practice of putting things into metric prefixes requires that you can use them fluently. This is a major objective in both forms of general chemistry here. You are likely to encounter the prefixes that are highlighted in red in your normal life, with mega through tera being primarily useful as you look at computer speeds and memory, and nano and pica being very useful for small concentrations. You can really think about each of these prefixes as being the equivalent of a scientific notation number. So if you want to move quicker between picomolar and molar, you can just replace the P prefix with 10 to the minus 12th. Easy peasy. Moving the other way just means that you need to get into an appropriate power of 10 and then swap the letter for a power. So if you wanted to change something into picomolar, you just need to make sure that it was multiplied by 10 to the 12th. We'll do some practice together in class. So now let's try to think about significant figure math. Suppose I look at a group of people and estimate that there are about 20 people. They're a strange group, and I'm not sure what has brought them together other than an unexplainable urge to congregate in large groups. I didn't count, and so 2 of the 20, remember I said there's 20 people, is an estimated digit. I really don't know the number to any more precision. Now I suppose a person left. His name is Gregor Samsa, and he never really formed any real connections with the group anyway. Hey, look, right where Gregor was, it was pizza. Pizza brought everyone together like a glorious beacon of peace. Anyway, I wouldn't suddenly know that there are exactly 19 people because I didn't know that there are exactly 20 people before. I'd still say that there are about 20 people. That's because you can't know the value of a calculated number to any more precision than the least precise number you have available. If I only know to the tens digit before, even if somebody leaves in the ones digit, if just Gregor leaves, I still don't know that any better. Turns out it actually works that way with all calculations. So the rules are whenever you're adding or subtracting numbers, the least precise number controls how precise the result is based on the decimal place of least precision. So here, the one number is only precise to the tenth digit. So the actual result is only accurate to the tenth digit as well. For multiplication and division, you are also limited by the least precise number, but now based on the total number of significant figures. So since the 2.57 shown has only 3 significant figures, the resulting product should also be reported to only 3 significant figures. Of course, if you're paying attention to significant figures, you're often rounding to the right number of significant figures. Never just stop at the last significant figure, always round based on the remaining decimals that you won't keep. So as a general rule, 5 or higher goes up and the rest goes down. There are more robust rules for rounding well for other calculations that we talk about in analytical chemistry. And as a quick teaser, here's what you have to look forward to. So it's one thing to say that we always keep the lowest precision of the numbers we add, but that can be more complicated when the numbers have different prefixes or powers of 10. Typically for addition, we will convert these all to the same power, typically the base unit, and then keep only up to the least precise value for addition and subtraction. So you can really only do addition and subtraction if everything's to the same power. On the top example, the 9.84 is known to the hundredths place, and so the answer is only known to the hundredths place as well. As indicated before, addition and subtraction are limited by the value of the last placeholder. So in this example, the placeholder happens to be in the thousandths unit. This is different than multiplication or division, where the lowest number of sig figs are preserved. In the second of these examples, the 2 sig figs in the 3.6 times 10 to the negative 19th limit the significant figures that are reported in the answer. You can see the limiting number highlighted in blue in each of these cases. So far, this may be review. You probably haven't thought about significant figures with logarithms, which are really important for pH calculations. The logarithmic number always has 2 parts. One of them is called the characteristic, the part before the decimal, and the mantissa is the part after the decimal. Only the mantissa is considered significant. So if you have a pH of 7.40, that only has 2 sig figs for the 40. As practice, add together these 4 numbers. I hope that you got 52.0. Now round every number to the ones digit and then add them together. If you are like me, you had a teacher tell you at some point that you should always round 5 up to the next number. If you actually do that, you can end up with a systematically larger number. In this case, it would give you 54 instead of 52. Instead, you should always round to the nearest even number because it prevents creating systematically high results, or even better, don't round until the very end of a calculation. In both our courses, water will play an outsized role for how we think about nutrient, pollutant, and analyte concentrations and mobility, how they move. As we know, the water cycle, also called the hydrologic cycle, plays a crucial role in getting water onto land by evaporating from bodies of water and then falling down as precipitate. On land, it's central to all life and in water. Therefore, it plays an essential role in the biosphere and in the anthrosphere. Rainfall precipitates many atmospheric molecules back to land, like we talked about sulfuric acid before. And groundwater affects how nutrients are transported in the geosphere. On the analytical side, water is the main solute that we'll be using in lab, and many of the samples that we are most interested in are analyzed as aqueous, that is, water-based solutions. So yeah, water is pretty important. There are many specific fields that study water. Hydrology is a broad field covering all studies of water, while oceanography is the study of oceans and limnology is the study of freshwaters. Chicago is a good place to do limnology right next to the largest liquid freshwater system in the world. There's, of course, other studies of water. Dr. S's husband is a fluvial geomorphologist. Fluvial refers to rivers specifically, and geomorphologist refers to the study of how the earth changes. So he studies how river shapes and currents deposit sediments and gradually change the riverbed and bank. Water has a few properties that make it particularly interesting. Most notably, water has incredibly strong hydrogen bonding capabilities for its size, with each oxygen being far more electronegative than hydrogen, which allows it to hydrogen bond very effectively. Moreover, each oxygen has two lone pairs to couple with the two other water molecules' hydrogens, allowing water to create complex lattices of hydrogen bonding in both liquids and solids. Water's strong hydrogen bonding explains many of its most important properties. For example, high surface tension, which is essential for plants to wick water up from the soil. You can see in the bottom two images that water molecules must align along the surface to maximize interactions into the bulk solution. So you can see that the edge of the water molecule is always facing the same direction, the oxygen. And since that does that, the molecules along the surface are held more tightly than the average interaction. That's what gives us, again, surface tension. Hydrogen bonding allows water to have high heat capacity as well, because the molecules can increase in kinetic energy without actually separating from each other, which is really important for regulating the temperature of the Earth. It also allows water to stratify, that is, form layers in lakes and oceans, which impacts currents and nutrient flow. Water is a particularly good solvent for polar and weakly ionic molecules, since it can form strong hydrogen bonds with polar molecules, as shown on the left. Or it can solvate ionic molecules, meaning the water molecules can minimize the impact of charges in solutions by spreading the charge over a larger area, which you can see in the model for sodium and chloride solvation that's shown on the top right. In fact, the very properties of water could be an entire class where we turn and worship at the wisdom and providence of our Creator. Water's unusually strong hydrogen bonding underlays every one of the properties listed here, except water's transparency. Since we're in Chicago, we care particularly about water here in Chicago, which is mostly fresh water and comes almost entirely from precipitation, from rainfall or snowfall. In fact, most of the access to water in the United States is fed by precipitation, everything but the coasts. And since most water used by humans is also fresh water, even the coastal areas tend to depend on precipitation. That's why you can have droughts in California right next to the ocean. But water isn't distributed evenly across the United States, meaning the types of water concerns in Chicago, like groundwater contamination from heavy industry, may look different from the types of concerns in Arizona, where lack of water prevents heavy industry, but groundwater tends to pick up more ground salts as reservoirs are depleted. This will shape both our environmental concerns, but also our analytical methodologies and challenges in each of those areas. There is some good news here. Since the 1980s, water use has decreased and stabilized, and actually has decreased in recent years, as shown in this public domain graph from the USGS, the United States Geological Survey. But the problem isn't overall use. It's actually that use has shifted to particular areas. You can see by the large purple swaths in the Southwest that much of our population, and therefore water use, has shifted to the continental Southwest. This is our very first chance to talk about honesty in data display. The Census Bureau image shows a percent change in population, which is generally helpful for seeing if areas are growing or shrinking. However, it's really misleading about overall changes in population in some places like California, where a small percent change may represent more change than the entire population of Montana or Alaska, let alone the changes in some regions of those states. So we care a lot about water, but we also care a lot about what's in our water, and depending on what it is, we may talk about concentrations a lot of different ways, depending on what we're measuring. The top 4 units on this page are all based on mole units, and they are particularly useful when an analyte, a thing that we're looking at, will undergo a chemical change. For example, it's really helpful to know the molar concentration for carbon dioxide that's dissolved in water, because it's always going to be in an equilibrium defined on a molar basis with carbonic acid. But look carefully, though, at that top row. In that top row, there are 3 different units that all have the same form for the units, an amount per volume of solution, moles per liter usually. So what's the difference then between formal, normal, and molar? That difference matters most with electrolytes, that is, substances that dissolve into ions. Molar should refer to concentrations of actual species, where the formal refers to the concentration of a collective species. So, like all forms of a polybasic anion, for example, carbonate plus bicarbonate plus carbonic acid, all of those should be making up the formal concentration. Normal allows us to account for concentrations of actual species, particularly acids and bases, based on an equivalence factor. For example, sulfuric acid, which is H2SO4, should give 2 times the concentration of H+, because there are 2 protons. The units in the bottom row deals with the types of concentration units that are typically used when we want to control an amount of something that probably isn't reacting a whole lot. For example, the concentration of ethanol in a beverage is usually given as a percent alcohol by volume, a volume percent. Or the concentration of lead in drinking water is usually given as parts per billion, hopefully. Or the concentration of carbon in steel is given usually as a mass percentage. The main focus of our next class will be working through examples of thinking through these unit conversions. For now, it's worth pointing out that in most cases within water, the things that we might want to measure are parts of dynamic processes, like equilibria, that make molar units the most convenient to work with. However, engineers hate molar units, and so most contaminant limits or design specifications will be given in mass percent units, or the closely related parts per million or parts per billion. This figure shows a number of significant types of reactions that can occur in water. For each of these, if we're truly going to understand how an element, ion, or molecule exists in solution, we really need to put these in molar units. Even movement within a solution is defined by equilibrium, which again is a newest concept for students who went through the Chem 101 route, but it's really important for understanding how molecules like oxygen move into water from the atmosphere. We have 3 layers in most water systems if they're not turning over. The top layer of water, the epilimnion, epi means above, and lim refers to the surface waters like limnology, is actually separated from the lower level, or lower layer, the hypolimnion. Again, remember hypo means below, like hypothermia or hypoxia. Those are separated by a thermocline, so a significant temperature gradient. That means the waters don't mix, and separate equilibrium are going to govern the sediments. We'll again mostly need to use molar units to deal with these types of things. And so anytime we have a reaction or an equilibria, we typically will use stoichiometric units, ones that are related to the actual quantities of molecules rather than just masses. Stoichiometric units are always in mole-based units, and we can really only do anything with them if we have a balanced equation. In natural systems that involve water, which would be the hydrosphere, much of the geosphere that we interact with, and the biosphere, the amount of freely available hydrogen ion, or H+, sometimes more accurately called hydronium, or H3O+, is a major factor in the behavior of all sorts of systems. However, the concentrations that we might encounter H+ at might be ridiculously high, like 12 molar, or they might be vanishingly small on the level of 10 femtomolar, which is, by the way, 10 times 10 to the negative 15th, or 10 to the negative 14th. If we use straight concentrations, it would be very difficult to compare. So instead, we use the pH scale. The pH of a solution is the negative log of its H+ concentration. So pH is the negative log of H+. You can also easily go the other way. So that means that 10 to the negative pH will give you the H+ concentration. And because pH is a log scale, only the significant figures after the decimal place for the pH are significant. So a pH of 1.55 has only 2 significant figures. We'll actually use the same type of power scale to make other values more accessible in this class as well. For example, we use pKa to describe the Ka values, or acid dissociation constants, on a more reasonable scale. We'll also use the power function to talk about electrochemical potential. A few more notes on tools of the lab. Not all reagents are the same quality. Reagent grade materials are relatively standard. They're controlled to a given purity and are used for reactions and making solutions. Some reagents are used to calibrate other reagents, though. Those are known as primary standards. These need to be controlled very carefully to ensure that they remain pure and are dry when measured, which in turn allows for accurate measurements of other solutions. For many types of instrumental analysis, reference standards are used, sometimes with mixtures that allow for internally calibrating an instrument at multiple signal locations. like several wavelengths for calibrating with several elements. There are also special purpose reagent grades that often have details appropriate for a specific use. For example, HPLC solvents are made to run on high performance liquid chromatographer instruments, or HPLCs, without impurities like water that would change the polarity of the solvent or impurities that would interfere with an instrument detector. So how do we choose what to use? We're always going to use the smallest bottle available. It's less likely to become contaminated. And we're never going to store the bottles open because you never know when somebody's going to sneeze in it. We're going to try to work on clean surfaces and make sure that caps never touch unclean surfaces. Otherwise, we'll have to do in lab what is called a ritual cleansing of that cap. Never return excess reagents to the original container. You could contaminate it. And if you can avoid spatulas in an original container, do so. Metal spatulas can be reactive, and plastic spatulas are hard to clean, so use ceramic when possible. And always try to keep a clean lab. A modern analytical balance actually measures force, like weight, not mass. Even more specifically, it measures how much current is needed to apply an appropriate force to keep the weight in the same spot. However, we always calibrate these based on mass standards, which is why we can measure mass with them. Because the current required to preserve that sample location is dependent on any drag in the balance, it's really important that the balance be clean, otherwise you might get a false reading. So clean up any spills immediately. The instruments also can drift, so it's important to re-zero or tare between measurements. There are several ways that you can take an accurate measurement. You may tare with a container so that the only mass that's recorded is the mass that's added. But this only works if you're going to take the measurement right away. So if you've got a beacon, you're going to measure into it right away. Otherwise, someone else might change the tare on the instrument, and it might, or the instrument might drift. It's actually a lot better to measure the mass of an empty container and then separately measure the full container and find the difference between those two. That way, you're always accounting for the drift and you won't be interrupted by another measurement. You can also take the mass of the container that you're measuring from before and after you remove sample, so measure how much you've removed. This is called weighing by difference, but it only works if you don't spill. So what are some ways that error might be introduced? You want to make sure always that you clean and tare the instrument. You want to make sure that you avoid things like fingerprints or moisture or air currents. You want to make sure the instrument is always properly calibrated. Many of the reagents we use are water soluble. That means that they like to actually interact with water. Sometimes they actually take up water from the air. We call them hygroscopic. If a reagent takes up water from the air, the mass will no longer be accurate unless we dry it. So we'll often use an oven to evaporate water and then a drying chamber called a desiccator to cool it down gently without introducing water. When we measure volume, we have a number of tools of varying accuracy. Just like we talked about in lab, volumetric flasks are usually best for fixed volumes. Burettes and calibrated pipettes tend to be the most accurate for variable volumes, like exactly 1.7 milliliters, when you don't have a volumetric flask for 1.7 milliliters. Micropipettes like those in the top right are fairly accurate if they are recently calibrated and very near the top of their volume range. I know that biologists like to use these all the time, but it's important to remember those limitations. Top of their calibration range and if they're recently calibrated. Syringes are actually better for very small volumes. Also, like we talked about in lab, the volume of a material is not fixed. If you're using volume for a primary measurement, it actually really matters what the temperature is. That's why it's important to use a temperature-based density to convert between volume and mass. Since we often dry materials in the oven, we'll need to let them cool completely for the mass to be accurate, around 20 minutes. If you take it out sooner, the air on the scale warms up, and then there is less mass on the scale, so you end up with a systematic error. When we clean, we need to remove both organic and inorganic contaminants. Organic contaminants are nonpolar, and so they require a detergent that also has nonpolar components, since like dissolves like. Inorganic contaminants tend to be polar and require DI water. Sometimes salts that have +2 or greater charges have limited solubility and actually need to be removed by nitric acid, which makes them more soluble. So in general, when we're cleaning, we want to start by washing with soapy water. That helps to take care of some of the organic components. Then we're going to rinse thoroughly with tap water. That helps to rinse off all the soap. After we've rinsed with tap water, we want to rinse with DI water. The DI water can remove some of the ions that came with the tap water, make sure that we end up with something that has very few ions. But if we need something that has absolutely no ions in solution, we want to follow that up by rinsing with a small amount of type 1 ultra pure water, which is the purest grade of water. We also have a tendency to want to dry things quickly. But if we dry things with air or paper towel, both tend to deposit particles onto the glassware. And so it's much better to dry with a flame or with an oven. In rare cases, organic solvents may be used and the process may be repeated. This is actually really common in organic where we rinse a lot of stuff with acetone, but it's pretty rare in this course.